This is Lecture 10, Bivariate Regression. By the end of this lecture, you should be able to interpret a regression coefficient, interpret a significance test for a coefficient, interpret a constant in a regression analysis, interpret a significance test for a constant in a regression analysis, calculate an estimate from a regression equation, calculate the errors from a regression equation, and interpret an R-square and an adjusted R-square. In the previous lecture, I showed you how to calculate a correlation coefficient between two variables. A correlation coefficient tells you the direction and magnitude of the relationship between two variables, but it does not distinguish between one variable being an independent variable and the other variable being a dependent variable. In addition, it does not tell us the specific impact of an independent variable on a dependent variable. Sometimes we want to know as the independent variable changes by 1, how much does the dependent variable change? In this lecture, I'm going to talk to you about ordinary least squares regression. Ordinary least squares regression tells you the specific strength of the relationship between an independent and dependent variable. It assumes that the independent variable has a linear effect on the dependent variable. In other words, it assumes that the effect of the independent variable on the dependent variable is the same across all values of the independent variable. Therefore, a change in the independent variable at small values of the independent variable and a change in the independent variable at higher levels of the independent variable have the same effect on the dependent variable. Ordinary least squares regression also tells us how much the dependent variable changes as the independent variable changes by 1. To illustrate the intuition behind calculating a regression analysis, I gathered data on the net migration of countries in 2010, the dependent variable, and the GDP per capita of those countries in 2009, the independent variable. I present the data in the scatter plot. When I run a regression on this data, the regression analysis creates a line that literally goes right through the middle of all of these observations. One way to formally represent a regression equation is to write y hat equals b hat times x plus a hat. Y hat is an estimate of the dependent variable, b hat is the coefficient, slope, or beta, x is the independent variable, and a hat is the constant y-intercept or alpha. Now imagine that instead of running a regression analysis, I tried to draw a line through the middle of these observations myself and tried to estimate the regression equation. The y-intercept, a hat, would be the value of y where the line passed through the y-axis. It looks like this line runs through the y-axis around the value of negative 200,000. So that will be our estimate of a hat. Next, the slope b hat is simply the change in y over the change in x. So I used the point where the line passed through the y-intercept and the point here and calculated the slope based on the values of y and x at these 2 points. Y went from 0 to 1 million. So for the numerator, I calculate 1 million minus 0. X went from 0 to 60,000. So for the denominator, I calculate 60,000 minus 0. B hat turns out to be 16.7. So my educated guess equation for the regression equation between these two variables would be net migration 2010 hat equals 16.7 times GDP per capita 2009 minus 200,000. Now that I have shown you the intuition behind a regression equation, I'm going to briefly show you how b hat and a hat are formally calculated. B hat is the sum of each x observation minus the mean of x times each y observation minus the mean of y, and that value divided by the squared value of the sum of each x observation minus the mean of x. All this is really trying to calculate is whether each x deviates from its mean in a similar manner to its corresponding y deviating from its mean. This is similar to the correlation coefficient calculation. A hat is simply the mean of y minus b hat times the mean of x. Fortunately for you, I am not going to ask you to calculate b hat and a hat in this course. I cover that material in Political Science 398. Instead, I'm going to show you how to run and interpret a regression analysis in SPSS. For this course, we will let SPSS calculate our regression equations for us. In SPSS, you click Analyze Regression Linear, you put the dependent variable in the dependent variable box, and you put the independent variable in the independent variable box. This is what a regression output from SPSS looks like. The first step in interpreting these results is writing out your regression equation. The equation is the dependent variable hat equals b hat times the independent variable plus a. We know that our dependent variable is net migration and our independent variable is GDP per capita. So we can insert that information here. Now we need to find b hat. All the information you need for b hat is located in the bottom row of this last table. The b hat is located in the B column 19.045. All the information you need for a hat is located in the top row of this last table. A hat is located in the B column. Yes, I know this is confusing. Negative 182,752.154. So our equation would be net migration hat equals 19.045 times GDP per capita minus 182,752.154. Note that I subtracted a hat because a hat is a negative number. Let's compare this equation to our educated guess. A hat is quite close, negative 200,000 versus negative 182,752.154. Our coefficient b hat was slightly off, but close as well, 16.7 versus 19.045. The next step is determining whether the coefficient, or b, is different from 0. If b hat is the same as 0, the independent variable has no effect on the dependent variable. If b hat is different from 0, the independent variable has an effect on the dependent variable. Positive, whereas the independent variable increases, the dependent variable increases. Or negative, whereas the independent variable increases, the dependent variable decreases. I am not going to teach you how to calculate whether a coefficient b hat is different from 0. Once again, I covered that in Political Science 398. But I will tell you the intuition behind the calculation. We use a t-test to determine whether a coefficient b hat is different from 0. This is similar to when we use the t-test for a difference of means test. We divide the coefficient b hat by the standard error of the coefficient. The standard error of the coefficient takes into account how well the regression model predicts real-world outcomes. If it predicts well, the standard error is small. If it predicts poorly, then the standard error is larger. Now recall that in a t-test, you want to calculate a large t-statistic because it means that the t-statistic is greater than or less than the t-value you get from the t-table in your textbook, and that indicates a significant relationship. The way to get a larger t-statistic in this equation is to get a model that generates good estimates, which leads to a smaller error, which leads to a smaller denominator, which leads to a larger t-statistic. Now that I have shown you the intuition behind a significance test for a coefficient b hat, I will show you how to determine whether a coefficient is significant based on SPSS output. The last cell on the bottom row of this last table here gives you a sig value for the coefficient b hat. To determine if the coefficient b hat is significant, follow these steps. Start with this first criterion here. If the sig value is less than 0.002, then the coefficient is significant at the 0.001 level. If the sig value does not meet this criterion, move on. If the sig value is less than 0.02, then the coefficient is significant at the 0.01 level. If the sig value does not meet this criterion, then move on. If the sig value is less than 0.10, the coefficient is significant at the 0.05 level. If the sig value does not meet this criterion, move on. If the sig value is greater than 0.10, the coefficient is insignificant and indistinguishable from 0. Going back to our example, our coefficient is significant at the 0.001 level, since 0.000 is less than 0.002. Now you may be wondering why these values here are different than these values here. These values are simply these values divided by 2. I did that because in SPSS, it does a two-tailed test of significance. For a coefficient b hat, but we only want one tail. A two-tailed test assumes you have no idea of how your independent variable should affect your dependent variable. But we generally always have an idea whether the independent variable should have a positive or negative effect. Normally, you're supposed to divide the sig values in SPSS yourself, but I did it for you to make it easier for you to interpret. So just follow these instructions I gave you in the slide. If you have a significant coefficient, you write, the results suggest that there is a significant relationship between the independent and dependent variables. You indicate whether that relationship is positive or negative based on the coefficient b hat. If the coefficient is positive, there is a positive relationship, and if the coefficient is negative, there is a negative relationship. Next you write, as the independent variable increases by 1 unit, the dependent variable increases or decreases by the value of the coefficient b hat. The dependent variable increases if the coefficient is positive and decreases if the coefficient is negative. So going back to our example, we would write, there is a positive relationship between GDP per capita and net migration. This relationship is significant at the 0.001 level. As GDP per capita increases by $1, migration increases by about 19 people. If the coefficient is insignificant, then you say that the results do not suggest that there is a statistical relationship between your independent and dependent variables. You cannot make any conclusions and you do not have support for your argument. Next, you have to determine if the intercept a hat is different from 0. The sig value in SPSS for a hat is at the end of the row here, the constant row. Start with this first criterion here. If the sig value is less than 0.001, then the intercept is significant at the 0.001 level. If the sig value does not meet that criterion, move on. If the sig value is less than 0.01, then the intercept is significant at the 0.01 level. If the sig value does not meet that criterion, move on. If the sig value is less than 0.05, then the intercept is significant at the 0.05 level. If the sig value does not meet that criterion, move on. If the sig value is greater than 0.05, then the intercept is insignificant and indistinguishable from 0. Going back to our example, our a hat is significant at the 0.01 level because 0.002 is less than 0.01, but is not less than 0.001. Note that I did not divide the sig values by 2 because, unlike a coefficient, we do not have an expectation of whether an intercept should be greater than or less than 0. So we use a two-tailed test. Next, you interpret the intercept a hat. Sometimes it makes sense to interpret it and sometimes it does not. A hat tells us the value of the dependent variable if the independent variable had a value of 0. So in this case, when GDP per capita is 0, net migration is predicted to be negative 182,752. This is unrealistic because no countries in the world would have a GDP per capita of $0. Now I am going to show you how to calculate a point estimate from a regression equation. You calculate an estimate for each observation. You only do this if the coefficient is significant. So we have this equation here. Net migration hat equals 19.045 times GDP per capita minus 182,752.154. We insert the value of the independent variable here. So let's say in observation 1, GDP per capita was 10,000. We would calculate net migration hat equals 19.045 times 10,000 minus 182,752.154, which equals 7,697.846. An estimate from a regression equation gives us an estimate for a specific observation. Sometimes we want to know how far our estimates deviate from the actual values of the observations. This is known as estimate errors. To calculate the estimate error, you take the actual value of the dependent variable for a specific observation and subtract the estimate from it. So in our previous example, the estimated net migration was 7,697.846. Imagine the actual net migration for that observation was 112,000. We would calculate 112,000 minus 7,697.846, which equals 104,302.154, our error. The last topic I'm going to cover in this class is how to interpret an R-squared from a regression analysis in SPSS. I cover how to calculate an R-squared in Political Science 398. An R-squared tells us the extent to which the variation in our independent variable estimates the variation in the dependent variable. In other words, how well does the independent variable predict the dependent variable? In the SPSS output, you can find the value of the R-squared in the model summary box here. An R-squared ranges from 0 to 1. Values close to 1 indicate that the independent variable estimates the dependent variable well. Values close to 0 indicate that the independent variable estimates the dependent variable poorly. In our example, the R-squared was 0.151. You move the decimal place over 2 places to the right and make this value a percentage. Then you state the variation in the independent variable explains the R-squared percent variation in the dependent variable. Or in this case, variation in GDP per capita of a country explains 15.1% of the variation in the net migration in that country. Last, the adjusted R-squared simply modifies the R-squared to take into account the number of observations and the number of independent variables. You calculate an adjusted R-squared by taking 1 minus the R-squared times the number of observations minus 1 divided by the number of observations minus the number of independent variables minus 1. What this equation does is make the R-squared smaller if there are a small number of observations or too many independent variables. Theoretically, if you have too few observations in relation to how many variables you have, you may not have adequate information to predict your dependent variable. So the adjusted R-squared punishes you for not having more observations. In the SPSS output, the adjusted R-squared is located in the model summary box here. In our example, the adjusted R-squared was 0.147. Like the R-squared, you move the decimal place over twice and make it a percentage. Then you state, after taking into account the sample size and the number of observations, variation in the independent variable explains the adjusted R-squared % variation in the dependent variable. Or in our example, after taking into account the sample size and number of observations, variation in the GDP per capita of a country explains 14.7% of the variation in the net migration of that country.